Hi, everyone. Let's now solve a system of three linear equations in three unknowns. And yes, this could be a lot more work. But overall, the steps are the same, and the overall flavor of the solution of this problem is the same. First up, write the augmented matrix. And perhaps even more so than before, you might want to write in the plus or minus ones, the zeros, where appropriate, and line up your like terms. For example, remember here that the blank here leads to a 0, right? And we have applied plus or minus 1 coefficients over here. Okay. So here's our augmented matrix. I'll read these off. Row 1, reading off the coefficients, and then the right-hand side. 2, 2, negative 1, 2. If it helps, I'll write the letters here. X, Y, and Z. Row 2, 1, don't forget the 1. If you see this and you think 0, you might want to write this in. 1, negative 3, 1, slash negative 28. Over here, negative 1, 1, 0, slash 14. Again, some people remove the slash, especially if you tend to stop at a bar and you don't do what you're supposed to do on the right side. Some of you may benefit from no slash. And again, over here, we have the right-hand side. So this is our first augmented matrix. What's our goal? Our goal is to get this form over here. We want ones along the main diagonal, zeros all below. Again, that's for row echelon form, which I do technically require. Typically require. And these can be wildcards. And again, you may perform this process appropriately and get one matrix. Your friend might perform this process another way and get another matrix. They might be different matrices. It's possible that you can get different row echelon forms that still work. They're still row equivalent. So first off, let's see here. So first off, we want a 1 in the upper left position. We want the 2 to become a 1. And there, whoops. We want the 2 to become a 1. And there are a couple ways you can do this. You could divide the top row by 2. That would work out, but then you get a fraction there. Not horrible, but you would get a fraction there. Actually, another thing we could do is that we can switch these two rows. Row 1 and row 2, which you can indicate with a symbol like that, or perhaps a bit more formally like that. I would understand this. Again, it's a matter of debugging so that if you get the wrong solution or I notice you get the wrong solution, we can look back and see what you did. So we switch rows 1 and 2, and don't forget to switch these two on the right-hand side as well. We get this. 1, negative 3, 1, negative 28. The old row 2 is the new row 1. The old row 1 is the new row 2, 2, 2, negative 1, 2. And we keep the third row, negative 1, 1, 0, 14. So we like the fact that we have a 1 up here. Now, these two boldface entries, we need to be what if we want row echelon form? We want these to be zeros. How do we do that? We're not allowed to multiply by 0. I don't see how switching is going to help us. So we're going to have to do that rescaling and addition method. So here's what we're going to do. Now, normally, we don't want to do too many operations before we write a new matrix, but you can perform the same type of operation multiple times if you're careful. So for example, we can do that rescaling and addition method to eliminate down this first column over here. So we can make that a 0 and make that a 0. We can perform those operations before we write the new matrix. Okay, so how can we use, say, this positive 1 to change this 2 into a 0? Actually, you could argue that it might be easier to use the negative 1 to change the 2, but let's use the positive 1 here. What would you multiply the top row by before you add it to the second row in order to make this a 0? You would multiply the top row by negative 2, at least temporarily. We're actually going to rewrite the first row in the next matrix, but temporarily, like over here, okay, we're going to take negative 2 times the first row and add it to the second row in order to make this a 0. Alternately, you could take twice row 3 added to row 2. For some people, that's easier, and you could do that. Maybe your friend did that. Okay, here we're going to take the old row 2, the 2, 2, negative 1, 2, 2, 2, negative 1, 2, and we're going to take negative 2 times the first row. So we get, okay, 1 goes to negative 2, negative 3 goes to positive 6, right? Negative 3 times negative 2 is positive 6. 1 times negative 2 is negative 2. And negative 28 times negative 2, I usually allow a scientific calculator on exams. That's 56. When you add down, that's why we multiply the top row by negative 2 so that we can add here. 2 and negative 2 gives us 0. 2 and 6 gives us 8. Negative 1 and negative 2 gives us negative 3. 2 and 56 gives us 58. That's going to be our new row 2. And if you wish, you could write the new augmented matrix. But why not save some time? And let's go ahead and change row 3 as well. Now, bear in mind, I would recommend doing this only down one column, to eliminate down one column. Don't start moving to other columns. So don't do too much at once. And definitely do not mix two different ERO types before you write the new matrix. But here, we're doing that same rescaling addition method, and we're doing it down. We're doing it for the purposes of eliminating down column 1. We can do both of these operations before writing the new matrix. By the way, remember that when we write the new matrix, we can use that row equivalent symbol. Okay, so we're going to now change row 3, and we can use row 1 to do that. So, well, I hope we're using row 1 because remember we changed row 2. That might be confusing. So let's take the row 1, all right, and add it to row 3 to make this a 0 over here in the new matrix. The old row 3 looks like this. I'll erase these. The old row 3 looks like this. Negative 1, 1, 0, 14. And then we're going to add row 1 to that. And we're not doing anything in row 1. We're just taking it straight up. 1, negative 3, 1, negative 28. We're taking 1 times row 1. Add, and we get 0. 1 and negative 3 is negative 2. Think Vegas. If you win 1 and lose 3, you've lost 2. That's kind of cheap in Vegas. But 0 and 1 is 1. 14 and negative 28 is negative 14. And we have the new row 3. Okay. Now we really better write the new matrix at this point. We're going to keep the old row 1. We like that 1 up there, remember. We keep the 1, negative 3, 1, negative 28. And then the new row 2 will be 0, 8, negative 3, 58. And the new row 3 will be 0, negative 2, 1, negative 14. Again, this here indicates row equivalence. The matrices are not equal in the sense that you don't have the same entries in the same positions, but they're row equivalent in the sense that they correspond to equivalent systems with the same solution set. Okay, now, we like the fact that column 1 is good. The 1, 0, 0, we like that. So we're now going to fix column 2. And generally speaking, we're looking kind of down and to the right here. We're still going to write these zeros, but I don't think we're going to use row 1 as part of any addition method, because then you're going to mess up these zeros down here. So we're going to tend to look over here. So for example, we're going to tend to use either row 2 to affect row 3 or vice versa. we'll basically leave, we'll basically leave row 1 out of it for now. Okay. Now, there are different ways of approaching this. The way I'm looking at this, in order to avoid having to multiply by 1/4 or something, I might want to use the -2 to knock out the 8, but then you're going to get a 0 right in the center when I'd rather have it down below. So I think I'm going to start by switching rows 2 and 3. You don't have to do that, but let's go ahead and switch rows 2 and 3 so that the -2 is here, the 8 is down there, and then the 8 will eventually become a 0. I'm kind of strategizing. If you don't like that, that's fine. All right. So remember, in the center position, we ultimately, I'll draw arrows. In the central position, oh, sorry, better color. What, brownish? Okay, 8, okay, 8, all right. Okay, so in the center position, the 8 here, well, instead of an 8 in the center, I'd like to have a 1 in there instead of a -2. I like to have a 0. Okay, but first, I'm going to switch the 2 rows here. Okay, which I've indicated here. Row 1, we keep the 1, -3, 1, -28. The old row 3 is the new row 2. The old here I had the 8 here, the -2 here. I'm going to wait, I'm sorry. This is the matrix we're working on. I just copied them. All right, going from here to here. Okay, so for this matrix, I just copied this matrix and I bold-faced the entries we want to change. So really, the strategy is now, okay, I want the 8. Well, I said this before, I want the 8 to be the 1, the -2 to be the 0. Okay, but then we're going to switch. So the old row 2 becomes the new row 3, and the old row 3 becomes the new row 2. Row 1, we keep the 1, -3, 1, -28. The old row 3 is the new row 2. So we get 0, -2, 1, -14. The old row 2 is the new row 3. 0, 8, -3, 58. Now we'll use a row replacement ERO to eliminate the 8. Okay, so by row replacement, that's another way of saying that addition elimination method. We're going to use the -2 to knock out the 8, make it a 0. All right, so the old row 3, the one that we're changing up on top here, 0, 8, -3, 58. What do I want to multiply row 2 by before I add it to row 3 as this temporary row over here? -2 times 4 is -8. That would be a good thing to add. So we take, I'm sorry, it's a +4 times -2 is -8. +4 times -2 is -8. Okay, so 4 times 0 is 0. I'll do this. 4 times 0 is 0. 4 times -2 is -8. 4 times 1 is 4. 4 times -14 is -56. Okay, and then add down, we get 0, 0, 1, 2. That's our new row 3. Let's replace the old row 3 with the new row 3. We're going to replace the old row 3 with the new row 3. And we get 1, -3, 1, -28. That's been there forever for row 1. Row 2, 0, -2, 1, -14. That's holding on from before. But row 3 is changing to 0, 0, 1, 2. So again, column 1 was good from a long time ago. All right. We like the fact there's a 0 here, and we get lucky. We get lucky that there's a 1 there. But even if that weren't a 1, eventually we could divide by, if this were a 3, for example, we could divide by it through this row. Okay, now who's left to change? Who's left to change? We got to change the -2. Make that a 1. Don't make it so hard for yourself. Divide by -2. Rescale. Divide by -2. 1, -1/2, +7. Okay, so I indicate that division over here. All right. Finally, we have our matrix in row echelon form. We have 1s along the main diagonal, 0s all below. So that ends the really tough part of the problem, right? And your friend may have ended up with a different matrix, but could still be correct. So that's the giant part of the work. Now it's automatic. We write the new system. These are the coefficients for x and y and z. All right. So we write the new system in terms of x, y, and z. From here, the first equation, x minus 3y plus z equals -28. Second row becomes y minus 1/2 z equals 7. Over here, z equals 2. We love the system. What shape is it? It's triangular. In particular, upper triangular. We have z equals 2. Great. Now be careful. You don't want these to look too much like each other. Here, I guess it doesn't matter, but I guess I would have written z equals 2. It's a good habit to slash your z's, all right? And then we do what? We back substitute. We take the value for z, plug it into here, and solve for y. And then we're going to take the values that we get for z and y and plug into the first equation to solve for x. All right. That's why we like to have 1s along the main diagonal, because then this is 1x, 1y, 1z. Although you could argue it might have been easier in some cases if you avoided the fraction there. But again, I was saying that for our version of GEBS, we should have 1s along the main diagonal, get row echelon form. I also want to teach you row echelon form. Okay, so when we do the back substitution, we know z equals 2. We back substitute y minus 1/2 times 2 equals 7. Y minus half of 2 is 1 equals 7. Add 1 to both sides. Y equals 8. Not done yet. Take those values for z and y, climb up the ladder. We plug them into here. So I'll clean this up a bit. All right. So y equals 8. It's plugged into here. Z equals 2, plugged into here. I guess if your z's and 2's look alike, it doesn't matter too much. All right. So we plug those in, right? Okay. X minus 3 times 8 plus 2 equals -28. X minus 3 times 8 is 24, plus 2 equals -28. In Vegas, you lose 24, win 2, you've lost 22. Add 22 to both sides, x equals -6. We're not done yet. Remember that the answer to solve a system problem is a solution set. And we need to indicate solutions, in this case, in the form of an order triple. Oh, so what's the order triple? What is the solution? Is it going to be 2, 8, -6? Is that going to be our solution? No, because that would be in the order z, y, x. That's wrong. That's the wrong order. You have to see, you solve for these unknowns in reverse order. You got to put it in the right order. So you got to reverse the reversal. You start with the -6, then the 8, then the 2. When you check your solution, you'll really see that. Again, remember that the order of the coordinates is the reverse of the order in which we found them in the back-sub procedure. A check is optional, but you'll feel really good if you see it working out. And really bad if it doesn't, in which case, debug. Maybe it was just a matter of reordering. Hopefully, it would be that easy to fix. You're lucky if it's just a reordering. Okay, check, optional. All right, and remember to check in the original system. X equals -6, y equals 8, z equals 2. Okay, we get, hey, 2 equals 2, -28 equals -28, 14 equals 14, all good. And we're very happy. And your neighbor might still be sad, might hate you. Okay, next up, when does a system have no solution?